Hello, my name is Jared Skeens and welcome to the Zoom room. Today we'd like to look at a past paper of the new 2020 syllabus. So May, June 2020 for Pure Maths 3. This is a Pure Maths 3 past paper, the first one, paper 31 of the May, June 2020. Notice a little bit of difference from the previous syllabus. The previous syllabus was 1 hour and 45 minutes. This is now 1 hour and 50 minutes. The total marks are still 75 points. So let's get right into it. Find the set of values of x for which 2 times 3 raised to the 1 minus 2x less than 5x. And we need to find the set of values of x. Notice set of values means inequality. And give your answer in the simplified exact form. So when you see the word exact, make sure that you do not convert it to decimals. You need to leave it in pi or e or radicals, but do not change it to decimal form. Now, if you noticed, I've worked it out 2 different ways. When I first did it, I worked it out canceling one of my logs with the base. I chose to use log base 3. You could have also chosen log base 5. And I worked it out and I ended up with this log base 3 of 6 over log base 3 of 45. And if you look at the answer key, it's ln of 6 over ln of 45 with an understood base e. They're actually the same answer. Remember, logarithms are proportional, so it doesn't really matter what the base is. So this 6 over 45, regardless the base of your logarithm that you happen to use. However, in working it out, after I worked it out this way on the left, and I was just curious how it would work using ln instead of log, and it did come out a little bit faster. So I'll go over this right side. If you want to, you can, look through the left side here and look at it. But if we look at the right side, right away we just ln both sides. And remember, with multiplication of the argument of a logarithm means you can change it to addition with two logarithms. So that's what I did, ln 2 plus ln 3 to the 1 minus 2x less than ln 5 raised to the x. Your x is an exponent, so it can multiply to the front. And the 1 minus 2x is an exponent, it can multiply to the front. And so distribute the ln 3 through, and then I took the 2 from the coefficient and I put it up as an exponent. Then we want all the terms with x in it on one side. So x ln 5 and then plus, because we have to add that over, x ln of 3 squared. I wanted the 2 as an exponent on the argument and not in the coefficient because I want the x's by itself in front. And on this side, the non-x terms on the left, so ln 2 plus ln 3. Again, addition means you can multiply, so ln of 2 times 3, which is ln 6. On the right side, we factored the x out, leaving ln 5 plus ln 9. And of course, addition again means multiply, so ln of 5 times 9. And we divide that to the other side, and we end up with our ln 6 divided by ln 45. So as long as you're properly using your laws of logarithms, it's not really that difficult to work through, and it was worth 4 points for that. Second question, expand 2 minus 3 to the x, or 2 minus 3x raised to the negative 2 power in ascending powers up to and including the x squared term, simplifying the coefficients. Again, we have a 4-point problem. This one is the binomial expansion, or not binomial expansion, sorry, just yes, a binomial expansion but it's an expansion with the exponent that is not a positive integer. So we need to get it into this form here on the right. A 1 minus something is what we want to get it into. So to get a 1 in the front, we divide out the 2. Then we need to distribute that exponent to the 2. So 2 to the negative 2 becomes 1/4. On the inside, that negative 2 is still the exponent of the inside. And notice though, when we factor that 2 out, you're dividing it out. 2 divided by 2 is 1. 3 divided by 2 is 3/2. So be careful with this second part that you remember that factoring is dividing. So you have 3/2 x. You distribute your exponent to the multiplication part. Then, so our 2 to the negative 2 becomes 1/4. So what we're expanding is this 1 minus 3/2 x to the negative 2. And basically you're following the formula that is in your formula sheet. So please refer to your Cambridge formula sheet, but it starts out with 1 plus n over 1 times that b term in that second term in your binomial, negative 3/2 x, plus n times n minus 1 on top and just 1 times 2 on the bottom. And the more you practice this, the more you'll see the pattern. The top number decreases by 1, the bottom number increases by 1. Then you have that second term again, the negative 3/2 x, this time squared, and all we have to do is go up to the squared term. That square distributes, giving us a positive 9/4 x squared, and this here in the front, the 2's cancel and we end up with a positive 3. So when we simplify, we get 1/4 in the front, 1 in the parenthesis, these 2's cancel and the negatives cancel, so we're left with 3x. And then over here, we have 3 times 9/4, which is 27/4 x squared. Distribute the 1/4 gives us 1/4 plus 3/4 x plus 27/16 x squared. So 1/4 plus 3/4 x plus 27/16 x squared is our answer. Again, follow the formula in your formula sheet. It does follow a predictable pattern with these terms that come from this 1 minus something in the binomial. Moving down here, state the set of values of x for which the expression is valid. Now what this is referring to is once you get your binomial into the 1 minus something here, or could be 1 plus or 1 minus, but 1 here and then something here, this second value, this 3/2 x, has to be less than 1. So when you solve this for x, the absolute value of x then has to be less than 2/3. In other words, if you want an accurate or at least a semi-accurate approximation, when you plug a value in for these x's, that value needs to be less than 2/3 in order for you to get a good approximation. So this is just something that you need, a detail that you need to know. It's only 1 point, but it is easy to do if you know where you're looking. Number 3, express the equation tan theta plus 60 equals 2 plus tan 60 minus theta as a quadratic equation in tangent, and hence solve the equation from 0 to 180. This is 6 points, so obviously it's going to take some work. Notice the domain statement only applies for first and second quadrants. And we are in degrees, so make sure your calculator's in degree mode. Now, tan theta plus 60 is an identity. Again, you can find this identity in your Cambridge formula sheet. And so this is the sum identity for tangent, or the positive one of the sum identity. And then over here we have the negative one for the sum identity, or might be called the difference identity. And then the 2 is just the 2. So we do follow the identities from your formula sheet. Then how you approach this is, I suppose there's a couple of different ways. I went ahead and calculated the tan 60 since it's a numeric value, got 1.732. Also at the same time, I multiplied both sides by the common denominator. So this one needs a 1 plus tan theta tan 60, and the 2 needs both of them, and this side only needs the 1 minus tan theta tan 60. So that's this long line here, and then multiply it all out to get this quadratic. Distribute your 2 through this binomial expansion here, and then expand these 2 here at the end. So you get this long one here. Just careful with your expansion that you follow the right distribution pattern. When you simplify this all out, it does simplify to nice numbers, 6 tan squared theta, which, by the way, this 1.732 is a root 3. That is root 3. So it might be easier for you to use root 3 since tan 60 does come from your special triangle. So if you want to use root 3 instead of 1.732, that would be fine as well. Anyway, you get the 6 tan squared theta plus 8 tan theta minus 2 equals 0. Divide that by 2 to reduce it down a little bit. This does not factor. The factors of 1 and 3 do not subtract to give us 4. So I just did the quadratic formula directly in my calculator. The quadratic formula, the negative b plus or minus b squared minus 4acl over 2a, and end up with this tan theta equals 0.21525. And then for the minus part, it's a negative 1.5486. Then inverse tangent both sides, you get 12.1. 12.1 is first quadrant in the positive direction. And we get a negative 57.147. Well, a negative 57 is a fourth quadrant answer. Tangent is negative in the second and fourth quadrant. So we want to move that 57 into the second quadrant. So we do 180 minus 57.147, and we get 122.9. So that is our second quadrant answer that is in the positive theta direction. And then, of course, our first quadrant answer was the 12.1. Moving on, the curve with equation y equals e to the 2x times sine x plus 3 cosine x has a stationary point in the interval 0 less than or equal to x less than or equal to pi, which, by the way, is radians. So make sure your calculator is in radian mode. Find the coordinates of this point, giving your answer to 2 decimal places. And our domain is also only for first and second quadrant. So stationary points means we need to do the first derivative and second, set it equal to 0. So this is a product rule. You have an x term in this e to the 2x multiplying by a parenthesis with x in it as well. So this is the product rule, 1d2 plus 2d1. So here's our 1, e to the 2x, d2, the derivative of sine is cosine, the derivative of 3 cosine x is a negative 3 sine x, plus 2, which is the sine x plus 3 cosine x, meaning the second term, d1. d1, the first term, e to the 2x. Well, e to the x is e to the x. So we get e to the 2x times the derivative of the 2x, which is 2. Then, when we set that equal to 0, obviously you can factor out an e to the 2x. However, an exponential cannot equal 0. In other words, you can't raise a base to any power and get a 0. So that factor basically just disappears, or you divide it into the 0 if you want it to go away. And then you are left with this remaining part. Don't forget to distribute your 2 through this sine x plus 3 cosine x. Notice we have both sine x and cosine x terms in our equation. So we want to simplify those based on sine and cosine. Move the sine to the other side, and then we're going to divide by cosine so that we end up with a tangent. That way, instead of having 2 trig terms in our equation, we just have 1 trig term. So we use our tangent to make sine divided by cosine. Becomes tangent equals 7, inverse tangent both sides. Again, don't forget to set your calculator to radians, and you get 1.43. Tangent is positive in the first and third, but the third quadrant is not allowed by our domain. Moving on, determine whether the stationary point is a maximum or a minimum. Normally, for determining the nature of the stationary points, I prefer to use the second derivative test. However, when we're working with more complicated trig equations like this, instead of trying to figure out what the second derivative would be, I just use the first derivative test. The first derivative test, we've already established the 1.43 as our stationary point. So just simply choose a value to the left and to the right of your stationary point. I chose 0 and 2. You don't have to go that far away. You could choose 1.42 and 1.44 if you wanted to. But I chose 0 and 2, and I plugged them into the first derivative. Remember, first derivative represents slope. So I plugged it into this first derivative and come up with 7 for evaluating at 0, and come up with a negative 208.69 when evaluated at 2. So since first derivative is slope, that means we have a positive slope coming up from the left to our stationary point with a negative slope following down the other side. So you can see that that makes kind of a mountain peak there. So that is a maximum value using the first derivative test. Now, question number 5. Find the quotient and remainder when 2x cubed minus x squared plus 6x plus 3 is divided by x squared plus 3. Well, this comes from further algebra section dealing with polynomials, and I prefer to use what's called synthetic division to do these kind of division problems. It takes less time. The only thing you have to learn is to keep your place values straight. So in other words, your cubic, quadratic, linear, and constant place values. Same thing with your x squared plus 3. So notice I take the coefficients, 2, -1, 6, and 3. We're dividing it by. Now when you use synthetic division, you have to change the signs of all the terms except the first one. So the 3 becomes -3. So starting from the back, moving forward, notice there is no x term, so I need to put a 0. And then if your first term has a coefficient of 1, you don't need it. You don't need to write it. So only if your coefficient was different from 1 on your first term, then you would put it down here and you would divide these numbers here by that coefficient. But our coefficient's 1, so we don't need it. So we bring down our first coefficient, 2. We multiply it by the end term here, -3, and that's -6. Now remember, this is 3 terms wide. Squared, linear, constant. 3 terms deep. So we need to go 3 terms deep and put -6. Then the 0 is 2 terms deep. 2 times 0 is 0. Add this column, we get -1. Negative 1 times negative 3 is 3. Negative 1 times 0 is 0. We have finished this. If you want to know where to put your remainder box, a cube divided by a square is linear. Okay, cubic divided by quadratic is linear. Power 3 divided by power 2 is power 1. So that means we need a linear value and we need a constant value. So the 2 is the linear, the negative 1 is the constant. After the constant comes your remainder. So our remainder happens to have two place values to it. The first one cancels out and becomes 0. The second one adds up to a 6. So now all we have to do is read the result. This is our linear, 2x, minus 1, that's the constant, with the remainder of a constant of 6. If there were a remainder in this 0 spot, it would have an x variable on it. So there are no x's, and there are 6 constants for the remainder. Moving on, using your answer to part A, find the exact value of this fraction, and we are integrating it from 1 to 3. So here's the integral with the bounds of 1 to 3. Notice I put the remainder here, 2x minus 1, or the quotient, plus the remainder, 6 over x squared plus 3 dx. So the first few here, first couple is just algebraic integration. Add 1, divide by that number, you get x squared. Add 1, divide by 1, you get negative x. Then this last one is part of the new syllabus material for this 2020 syllabus cycle. And this follows, it's in your formula sheet for Cambridge, so make sure you look at that. And it falls under your inverse tangent. So just look for it in your formula sheet, and you can see that it's x squared plus a squared, which means a is root 3. And you get your top number over a, inverse tangent with x over a. And so this is what you get here, evaluated from 3 to 1. Remember, do top minus bottom. So when we plug in the 3 minus when we plug in the 1, then you can start simplifying it out. Remember, it says find the exact value. So please don't change anything to decimals. So that means you have to evaluate a little carefully here. So when we get to this point, you see that your inverse tangent is with a root 3, and on this side, a 1 over root 3. Hopefully that sparks in your mind remembrance of your special triangles. So one of your special triangles follows the 1, 2, root 3, and the other one follows the 1, 1, root 2. But this one follows the 1, 2, root 3. So if you look at your special triangle, which is, by the way, your 30, 60, 90 special triangle, you will see that this one is your 60. But remember, we're dealing in radians because this, how do we know it's in radians? Well, we use radians because honestly, we don't want to deal with the degree unit. Radians is a non-unit unit, so you don't really have to worry about the unit with radians. So again, here's your 1, 2, root 3 special triangle. So root 3 over 1 would be your 60 degree for tangent, and 60 in radians is pi thirds. Your 1 over root 3 would be your 30 degrees, which is pi 6. And that helps it to simplify a little bit better. You can use your calculator with these fraction and radical coefficients, and you get 6 plus root 3 over 3 pi, which if you, I think I would have left it like this. I think in the mark scheme, it puts it as 1 over root 3. So if you just divide this radical back down, instead of rationalizing the denominator, you drive radical back into the denominator, and you get 1 over root 3 pi plus 6 is your exact answer. Now here we have number 6. We have one of these arc type questions, sector area and arc length. Says you can read through this question here, but the important equation is this last statement: the area of the shaded region is equal to the area of the circle. Well, so we have to show that we can get the equation tan x equals pi plus x. Well, we know the area of a circle is pi r squared. And our radius is r in the diagram. Also, if you notice, if we split this diagram in half, then we can call that part of the angle just x instead of 2x. So pay attention whether you're dealing with a part here or with the whole angle. So this is pi r squared. Now, the area of the shaded region, well, the area of the shaded region is going to be these two triangles, all the area of these two right triangles, minus the area of the sector area here in the circle. So, first we need to find the length of one of these sides. So tangent of x, here's x. So coming from the perspective of x, this is opposite over adjacent. So tan of x equals AT divided by r. Therefore, AT equals r tan x. You could write r tan x up here. Since this is a right triangle, then that means you're going to have 1/2 base times height. So 1/2 the base is r tan x times the height is r. So that gives you r squared tan x. You would have a 1/2 in front, except there are two of these triangles. So 2 times the 1/2 cancels the 1/2, giving you just r squared tan x for the area of these two triangles here, right triangles. Okay, so try to follow that through. This is the base. Here's the height, the r, and 1/2 base times height, but there are two of them. Minus the sector area of this part here. So sector area is 1/2 r squared theta. Well, now we're doing the entire sector area. So the angle is 2x. So again, the 1/2 and 2 cancel, leaving an r squared x. Notice there's an r squared in all the terms, so we divide that out to make it disappear. Notice there's no r in our equation, and when that reduces down, you get x equals tan x minus x, and you just have to rearrange it into the form that they have. Solve for tangent, so tan x equals pi plus x. Moving on, this equation has one root in the interval between 0 and pi halves, verified by calculation that this root lies between 1 and 1.4. Now don't forget, when you're verifying about a root, sometimes this is referred to as a decimal search. When you are doing this decimal search or verifying that there's a root, you need to set your equation equal to 0. It doesn't really matter which way you subtract your values to, but you need to move everything over to one side or the other. I chose to do tan x minus pi minus x equals 0. Then we evaluate this equation for the value of 1 and 1.4. So our function evaluated for 1 is a negative 2.584, and the function evaluated for 1.4 is 1.256. This, and I'm assuming it's a function, maybe it's not, I don't know what the graph looks like, but I'm assuming this is a function, and you evaluate this for 1 and 1.4, you get these two values, and you make notice that there is a sign change. One is positive and one is negative. Therefore, the root lies between the 1 and 1.4. Use the iterative formula to determine the root. We want to find out exactly what that root is. Correct to 2 decimal places. So now we use this form up here that they provided. This is basically an x equals f of x form, and give the result of each iteration to 4 decimal places. So I'm just going to start with 1, which is the first one that we had up here. And when you plug that into the right side, you come up with 1.3339. Then you plug that back into the right side again, and you end up with 1.3510. And I probably went an extra step further than what I needed to. We only need to go to 2 decimal places. And so there's enough evidence here to show that the root of x equals 1.35, accurate to 2 decimal places. Number 7, f of x equals cosine x divided by 1 plus sine x. Show that the derivative is less than 0 for all values of x between the interval of 3 pi halves and negative pi halves. I think that this domain statement probably has something to do with the vertical asymptotes in the denominator, not really affecting our solving process, but that's okay. So first derivative of this function, this is the quotient rule. We have this fraction with an x term on top and x term on the bottom. So we need to use our quotient rule, which is low d high minus high d low over the square of what's below. So hopefully you can follow that. And then you simplify it. And notice that this sign, if you factored out a -1, you would have sine squared plus cosine squared, which is 1. And notice the negative was factored out, so you need to keep that negative. And so that simplifies it a little further. Then if you factor out that negative, and you'll notice that the 1 plus sine x can then cancel with one of the ones on the bottom, and that leaves you with the -1 over 1 plus sine x. Now, how does that help us? Well, when you're trying to validate something being always positive or always negative, in this case, less than 0 is negative, you need to remember that your trig functions, especially sine and cosine, they oscillate between 1 and -1. So the maximum values and minimum values that sine can take is a 1 or a -1. Well, if you put a 1 in here, you're going to get a -1/2. If you put a -1 in here, you actually can't. Notice there's not the equal to sign on this side because you can't have a 0 here. So you can approach that -1, but you can't actually reach it. So all the values in between here are going to end up with this fraction always being negative or less than 0. Okay, so you want to use evidence that you're putting 1 to -1 in your simplified fraction and can demonstrate that it's negative. Part B, now we want to integrate this function from pi halves to pi 6, or actually from pi 6 up to pi halves. Give your answer in a simplified exact form. So here again, we have to work with exact values, so don't use decimals. And if you notice the integral of this, hopefully you recognize this as an f prime of x divided by f of x. Okay, f prime of x divided by f of x. So if the bottom is f of x and you derive it, you get the derivative on top, which is true. Therefore, we're dealing with a logarithmic integration. And so you just get the logarithm of the denominator, 1 plus sine x, and then we evaluate it pi halves and pi 6, top minus bottom. So here's the top plugged in. Sine of 90, or sine of pi halves, is 1. This is sine of 30 is 1/2. So hopefully you recognize that or plug it into your calculator. So what that leaves us with, 1 plus 1 is ln 2. 1 plus 1/2 is ln 3/2, and we are subtracting them because of top minus bottom. And then remember that subtraction with logs of same bases means division for the argument. So 2 divided by 3/2 leaves us with ln of 4/3. Going on to question 8. A certain curve is such that its gradient is at a point xy, is proportional, so don't forget your proportionality constant, to y divided by x root x. The curve passes through the points with coordinates 1, 1, and 4e. By setting up and solving a differential equation, find the equation of the curve expressing y in terms of x. Notice that it says the gradient. Well, gradient or slope is dy over dx, change in y over change in x. So that's our differential part of the differential equation. And it says that this gradient is, so notice this at a point xy is just a prepositional phrase. So your gradient is dy dx equals proportional. Don't forget the proportionality constant. That's extremely important. Y over x root x. So this is what we want to integrate, but before you integrate, you need to separate your variables. So with the dy, we want the y. So we divide the y over to the other side and get 1 over y dy. We want to multiply the dx to the other side. So here's our dx. I chose to leave the constant on the right side. It really doesn't matter which side you put it. I just left it on the right side, probably the easier way. And then the x's I joined together into exponent form. So x root x is actually x to the 3/2. And then because it's in the denominator coming up, it makes it a negative 3/2. So this allows us to integrate using our algebraic exponent rule. So 1 over y is actually ln y when you integrate it, equals, here you have to add 1 and divide by that number. So when you add 1, you get a negative 1/2. When you divide by a negative 1/2, it means you're multiplying by a negative 2. So you get a negative 2k x to the negative 1/2 plus c. Don't forget to put your plus c because we don't have bounds of integration. It's an indefinite integral. Then we take our value here, 1, 1 for our x and y. So when you plug in a 1 for x, you just get negative 2k. When you plug in a 1 for y, you get ln 1. Remember, ln 1 is 0. So in other words, e raised to what power gives you 1? E raised to the 0 power gives you 1. So that's 0 equals a negative 2k plus c. C therefore equals 2k. Since we're solving for 2 variables, that's why we need the 2 coordinates. So now we plug in the 4 and e. So now we have ln e equals, and we plug in a 4, and ln e, the ln and e basically cancel and leaves us with the exponent of 1. And on this part, 4 to the 1/2 is 2. That negative means we're dividing by 2. The 2's cancel, and you're left with a negative k, and then plus c. So c therefore equals 1 plus k. Now we just use these 2 equations here. 2k equals 1 plus k. K equals 1, therefore c equals 2. So now we can plug that back in and get our equation. Ln y equals a negative 2x to the negative 1/2 plus 2. But it wants us to solve this expressing y in terms of x. So we need to get y by itself. So we e both sides. And if you e both sides, You can either leave it like this, where your E has kind of this complicated exponent statement here, or this plus means when you're adding exponents, it means you're multiplying like bases. So you can also put the E as base to the 2 and move it out front as the coefficient. So either one of these two forms would be fine. Moving on, we get to part B. What happens to y as x tends to infinity? Well, if you come back here and you put infinity into x, well, square root of infinity is still infinity, and infinity in the denominator of a fraction drives the fraction to 0, and e to the 0 is 1, therefore you're just left with e squared. So as you approach infinity, y approaches the value of e squared. It's worth just 1 point. You expect to basically mentally figure that out. Now we go into vectors. With respect to the origin, the vertices of a triangle ABC have position vectors OA, OB, and OC accordingly. Use a scalar product. Show that angle ABC is a right angle. Make sure when you're working with these angle ABC and you're going to be using a dot product, make sure that you either work from the outside in or from the inside out. In other words, use AB and CB or use BA and BC. Okay, if you don't work from outside in or inside out, if you just go straight across AB, BC, you're going to end up with a sign problem in there. So make sure you work inside out or outside in. I choose to work outside to the middle because the V is the vertex of this angle. So I do AB. So if I do AB, that means B minus A gives you 1, 2, and negative 2. 3 minus 5 is the 3, or first this 3 up front, the i's. 3 minus 2 is 1. 2 minus a 0, there's no j's, is 2. And 3 minus 5 is negative 2. Then do CB, which means B minus C. You get 2, 1, 2 as your column vector there. And then we need to do the dot product between these. So 1 times 2 plus 2 times 1 plus negative 2 times 2. And that simplifies down to 0, meaning that on the right-hand side where you have that cosine, has to be cosine of 90 in order to get the 0 for the right-hand side of your dot product. Therefore, you're dealing with a right angle. So basically, you just need to show that your dot product comes out to 0, and that implies that you have a right triangle or right angle. Show that triangle ABC is isosceles. Well, so I just took the magnitude of A, since I have AB up here, just find the magnitude. So 1, 2, and negative 2, you square them and put them into this like extended form of the Pythagorean theorem. So 1 squared plus 2 squared plus a negative 2 squared square rooted. And that comes out to square root of 1 plus 4, which is root 9, which is 3. Then if you do CB and work that out, you also get 3, which those are the same. And if you find AC, which I didn't have yet, had to find AC separately, C minus A comes out to 1, negative 1, 1, and negative 4. And when you work out the magnitude of that, it's root 18, which is different from the other two. Therefore, since those two are the same, the 3's, you have an isosceles triangle. Part C, find the exact length of the perpendicular from the origin to the line that goes through BC. So here's our equation of a line through B and C. So with B and C, I chose to use C, 1, 1, 1, as the point. And then if it's through BC, then I used C minus B, I think. The CB, actually I used the CB, 2, 1, 2, as the direction. So you need a point and a direction. So R equals 1, 1, 1 as the point plus lambda or mu or whatever variable you want here times the direction 2, 1, 2. So I draw out a little picture here. Here's the line BC. Here's my point C, point 1, 1, 1. Here's the origin 0, 0, 0. And I want to find the straightest, shortest distance between origin and the line. So I'm going to call that N for normal because it's perpendicular. And the first thing I want to find is, by the way, there are 2 ways of doing this, or at least 2 ways that I know of. There is another way of doing this that is a little faster. However, I prefer to do it this way. It's a little bit longer, but it uses all the things that you learn about vectors in the Cambridge syllabus. For example, you learn, you use magnitude, you use unit vector, you use dot product. So everything that you're using in the vectors unit of study, you use here in this question. So that's why I prefer to use this method. It's a little bit easier to remember, although the other method, there is another method that is a little bit faster to do. So you might want to look up a second method of doing this type of problem if this method is a little bit confusing for you. So the first thing I do is I find the distance between O and C, and it comes up to right here, the magnitude OC is √3. The reason why I do that is because at the end, we're going to use the Pythagorean theorem to find out this length ON. But we have to work our way around the triangle. So I put in a little theta there. And over here on the right, I show kind of like the proof of what we need to do. So starting with theta, cosine theta is the adjacent over the hypotenuse, which is OC. And when you work it through, here you see that you end up with a form very similar to the dot product. So what we're going to do is just throw in a little 1, which corresponds to our unit vector. And this side here now exactly fits the right side of the dot product. So if you look at the left side of the dot product, it's this one right here, OC dot, the unit vector. So what we need to do is find the unit vector. And so our unit vector is the direction divided by the magnitude. So the direction here of 2 squared and 2 squared plus 1, that one we already did up here somewhere. The magnitude of it, or maybe we didn't, but the magnitude, maybe I just did it in my head because it's quite easy. 2 squared and 2 squared, that's 4 and 4 is 8 plus 1 squared. So plus 1 is 9 and the square root of 9 is 3. So we want to divide our direction, the 2, 1, 2, divide that direction by its magnitude, and that creates what's called the unit vector. So the unit vector is in the same direction as Cn, but with only a magnitude of 1. If you did the Pythagorean theorem with these fractions here, you would come up with 1. So that's what a unit vector is. So hopefully you already learned that, and now you're just practicing it on the test. So here is the point on the line. That's our point OC. So our O to C is 1, 1, 1. And then multiplied by, or not multiplied, but unit vector, dot product, the unit vector, 2/3, 1/3, 2/3. So when you multiply 1 times 2/3 plus 1 times 1/3 plus 1 times 2/3. Since they were all multiplying by 1, quite easy to just add it up right here. 2/3 plus 1/3 plus 2/3 is 5/3. So that means Cn is equal to 5/3. That's this length up here. Cn is 5/3, and we have a √3. Now all we have to do is do our quadratic formula. So Cn squared plus On squared equals OC squared. OC remembers the hypotenuse. So Cn is 5/3 squared. Our OC, we already saw, is root 3. Squared is then 3. So solving for ON, we get ON squared equals this. Square root both sides. ON equals root 2 over 3. Again, remember, it wants the exact length, so don't use decimals. Root 2 over 3. Number 10, we get into complex numbers. A complex number U is defined by U equals 3i divided by a plus 2i, where a is real. Express U in the Cartesian form x plus iy, where x and y are in terms of a. In other words, they don't want fractions, they don't want this big fraction here. You can have individual fractions, but we need to basically rationalize the denominator. So since we have I, our a plus 2i, we're going to multiply top and bottom by a minus 2i. So when we multiply by a minus 2i, we get 3ai minus 6i squared over a squared minus 4i squared, which reduces to the 6 plus 3ai over a squared plus 4. So the denominator, remember, distributes to the numerator. So the a squared plus 4 distributes to both components on the numerator, to the 6, which is the real value part of our complex number, 6 divided by a squared plus 4, plus, and then distribute it to the right-hand term here. So the 3a is the coefficient part over a squared plus 4, and then the I shows it that this is the imaginary part. So here we have it in terms of a. Moving on, find again the exact value. Have been having a lot on this test of exact value of a, for which the argument star, argument raised to the star, equals pi thirds. Now that star means we're talking about the conjugate, not the original u. The original u, remember it said that a is real, and when you, this, I don't know, maybe I'm kind of assuming a is positive, but basically when you look at this, if you look at a as being a positive number, you would be going to the right on the real axis and then up on the imaginary axis. Okay, so over and up. So the conjugate is going to change directions. It's going to go over and down, meaning instead of having a pi thirds, your argument is going in the opposite direction, so we can call it negative pi thirds. And then remember also that your argument is related to tangent, because tangent is opposite over adjacent. So the opposite part would be the imaginary part, or the 3a over a squared plus 4, divided by the adjacent would be the real axis value. So the imaginary divided by the real, the opposite over the adjacent. And so the a squared plus 4 cancels. You're left with 3a over 6, which reduces to a halves. Then to get rid of the inverse tangent, you tangent both sides. And the tangent of a negative pi thirds, again, you can use your special triangle using degrees for pi thirds. This is your 30, 60, 90. So it ends up giving you a negative root 3. So pi thirds is 60. You're coming from this point of reference of opposite over adjacent. So you end up with a negative root 3 over 1, or a negative root 3 equals a over 2 multiplied by 2, and you get a equals a negative 2 root 3. Moving on to the sketching part. On a sketch of an Argan diagram, shade the region whose points represent complex numbers z, satisfying the inequalities absolute value of z minus 2I less than or equal to the absolute value of z minus 1 minus I, and the absolute value of z minus 2 minus I less than or equal to 2. Now, what you want to do here is, first of all, you want to recognize your graph types. So this one on the right is a circle, and this one on the left is basically a perpendicular bisector. And so what you want to do is get z minus something. So z from, the minus is kind of like a from, z from, and when you factor out that negative, you get 2 plus I. That's going to be your center with a radius of 2. So here's our radius, or here's our center, 2 plus I, over 2 on the real, up 1 on the imaginary. So actually, I probably should have put R over here and I up here. I didn't even put numbers in. I probably should have made that a little more clear. R on this for the x-axis, I for the y-axis, and these are going by 1. So 1, 2, 3, 4, 1, 2, 3 for the i's. So here's 2, 1, or 2, and then I is our center with a radius of 2 going in all the directions, and there's our circle. Then we have a perpendicular bisector. Again, we want to get this z minus, so z from 2I and z from 1 plus I. So the 2I is right here. This is the dot, up 2I on the imaginary axis. And then 1 plus I is this dot right here, over 1, up 1. So that's our 2 dots. So notice I drew a little faint line between it. And notice this has a -1 slope. So perpendicular will be a +1 slope. And so you find that midpoint there and draw a +1 slope through it. So this line is this perpendicular bisector right here. If you want, I do have a video in my video series. I have videos on, or a video on sketching Argan diagrams, where I specifically get into showing how the little vectors work. You don't actually draw the z vector on here. What you're showing are the spots that the z vector can go to. You're not actually showing the z vector itself. So if you want a little bit more of an explanation with visuals, you can go to my video on the sketching the Argan diagram in complex numbers. So here's our graph. Now it says shade the region whose points represent. Notice it's less than the radius. That means inside the circle. And it is less than, meaning it's closer to the 2I. The 2I is less than, or it's closer to the 2I than it is to the 1 minus I. So if we're inside the circle and closer to the 2I than to the 1 plus I, that's this little region right here that's being shaded. Then we want to calculate the least value of argz for the points in this region. So remember, your argument comes from 0 degrees and rotates counterclockwise up. And so if you rotate from the x-axis upwards, the least value is going to hit at this point right here. If you wanted the maximum value, it would be straight up and down with the y-axis. But the least value hits over here, this far point. That's going to give you the smallest angle, which is going to be your argument. So basically, all you need to do is find yourself a nice little triangle in there. So I just come from that point down to the x-axis, the real axis. And you can count, it's 3 down and 2 over. So that's tangent theta equals 3/2, inverse tangent, and you get either 0.983 if you're dealing in radians, or 56.3 degrees if you're dealing in degrees. And that's the end of our past paper. So this is the first, paper 31 of the new syllabus series for May, June 2020. And I hope that this helps you work through it. And of course, you can look at my video series that goes through lesson by lesson through the entire A-level math books. And again, let me come back here to the screen. Thank you for joining me in the Zoom room, and hope to see you again next time.